Good morning. In today's lecture, we'll talk about the ways to prepare alkenes. Alkenes are very useful compounds, both as industrial feedstocks and as a small molecule pharmaceutical product. And therefore, multiple ways to prepare alkenes are needed. And we already seen some of these ways from a mechanistic perspective when we talked about T1 and E2 reactions. But today we will talk about these reactions in more of a synthetic context. And we will start with the reactions we already know, and these will be eliminations from alkyl halides. We've already seen two of these reactions. We've seen the E1 reaction and the E2 reaction. E1 reaction would operate with any kind of base. It requires a good leaving group. It's a two-step reaction which proceeds through a cation. And because it proceeds through a cation, it's stereochemically random, and it's subject to rearrangement. It also often competes with SN1 reaction. On the other hand, the E2 reaction requires a good base. It's a single-step reaction. It is stereospecific. And because it's a single-step reaction and does not involve a cation, it is not subject to rearrangement. And it's pretty easy to see that because of all these things, E2 reactions give more predictable products, and therefore synthetically they're more useful than E1 reactions. Let's look at the E2 reaction once again mechanistically. The reaction starts with the base, the base will react with this anti-periplanar conformation of our starting material. So if these are our substituents, R1, R2, R3, and R4, the base will abstract this hydrogen, which will then form the double bond and finally eliminate the bromides to give BH plus Br minus plus an alkene. But in the alkene, the relationship between the substituents, which was present in this anti-periplanar conformation, will remain preserved. So R2 and R4 when on the same side, and they will remain on the same side, and the same applies for R1 and R3. And this is what we call a stereospecific reaction. Now, in order to avoid the competition with SN2, the best thing to have would be tertiary substituents, because they can still undergo E2 reaction, but SN2 reaction is virtually stopped. And if that is not possible, then the use of hindered bulky bases helps a lot. And so example could be this reaction where we have our T-butyl bromide, and we can react this even with a weak base because it is unlikely that SN2 reaction will occur, and corresponding isobutylene is obtained in more than 90% yield in this case. And this is simply explained because T-butyl bromide is bad for SN2 reactions, but it's still very good for E2 reactions. That will be, I guess, use of the tertiary substituents. So we talk about hindered bulky bases. We would use things like potassium T-butoxide, or lithium diisopropylamide, also known as LDA, or things like triethylamine, which is a very cheap, easily available base, or even something like this, the dimethylpyridine. An example of a use of a hindered base would be some substrate which is less crowded. So if we have this secondary compound, if we treat this with t-butoxide, we will get our alkene as desired, and this will be an E2 reaction. But if we treat it with hydroxide, we will get some E2 reaction without doubt, but probably most of our product will come out of SN2 reaction, where this hydroxide acts as a nucleophile rather than as a base. Now, in terms of regiochemistry, and again, regiochemistry is a positional isomerism of double bond, the dehydrohalogenations follow the Zaitsev's rule, which guides them towards more substituted alkene, because these alkenes are thermodynamically more stable. So if we have a methyl group here, then using, say, ethoxide in ethanol, we will get some of elimination from this side. To give us 71% of this Zaitsev's product. But majority of our material will actually come from, minority of our material will come from a reaction which gives a so-called Hofmann product, which is less substituted. And as we know, this product is thermodynamically less stable. But one can think about it, and if you use a base which is really very bulky, such as the t-butoxide, then a bulky base will have a less strong of a preference for such a product, because it will have a harder time getting to these sterically hindered hydrogens. So in the case of t-butoxide, the same reaction, we switch this, and now with the Hofmann product predominates at 72%. And because the attack of the base occurs at the less sterically hindered position. As we mentioned, the E2 reaction is stereoselective, which means that the stereochemistry stereospecific, which means the stereochemistry of the starting material critically determines the stereochemistry of products. So to illustrate that on an example, here is a structure of a starting material in its Fischer projections, which is nothing more than this in a perspective formula. But again, if we remember that this eclipsed conformation is not the one reacting, instead we need to rotate this to get to the anti-periplanar arrangement, which is the one shown here. Now the base can attack this hydrogen, which will then eliminate the iodide, and the final product will have hydrogen and methyl group remaining on the same side as the double bond, and phenyl groups being on the same side as the double bond. In this case, this will be the Z product, and this is the only product because the reaction is critically determined by this transition state to give only the Z product. If we wanted to get an E product, we couldn't do this. We could have to switch our starting material to something, to actually a different compound, different stereoisomer of the starting material. And if we had this thing, then this would lead to E product. And so this is a very desirable behavior for a reaction because it allows us to generate either of the two isomers simply by choosing the appropriate starting material. I think seeing these relationships is sometimes a bit tricky, and that's why people develop a couple of ways to look at them. And the one that I like sort of uses the Newman projection formulas, which we've already seen when we talked about conformations of butane and other alkanes. And so if you look at this compound that is going to be subject to our elimination, this in Newman projection formula, as we already seen, will look this way. There will be hydrogen here and phenyl group here, and on the back carbon we'll have hydrogen on the bottom, methyl group here, and a phenyl group here. And the base will simply attack this hydrogen, which will then eliminate the iodide. But what we see at the end is simply this Newman projection formula sort of flattens out without changing the relationship between the substituted groups. So phenols remain on the same side and methyl group and hydrogen remain on the same side. So this can be viewed sort of as elimination of the two groups, dehydrohalogenation, and flattening out of the remainder of the Newman projection. This now works equally well in cyclohexane-based systems. So if we have this substituent, this arrangement of substituents, this is anti-periplanar and this is good. Even though this is the diaxial conformation with respect to these two groups. On the other hand, the more stable diequatorial one would be gauche, which is actually bad for this reaction. And so this will be a more stable thermodynamically, but unreactive conformation. This is diequatorial. Now, of course, these things switch through chair flip, and therefore most of the cyclohexane-based systems can actually get the conformation that is required for elimination. But it is worthwhile noting that if we have a system where we have like labeled groups such as these two deuteria and say bromine in equatorial position, this conformation will not eliminate because bromine is equatorial. So it will need to rig flip into the less stable conformation where bromine is now axial, but it will make the deuteria equatorial, and so the bromine will eliminate, but it will eliminate with one of these two hydrogens to give us technically two enantiomeric products, this one through elimination of the hydrogen that is closer to us, and this one. So again, we see here how selectivity plays a role, and selectivity is once again, to repeat that, is very desirable in synthetic chemistry because that allows us to get a single product when multiple products technically would be possible. Now, E2 reaction is not the only elimination from alkyl halides that is used for getting to alkenes. The vicinal dibromides are often eliminated as well. The original vicinal dibromide elimination actually occurred through a fairly interesting mechanism when the iodide would basically do an elimination of bromine, and so then reconstitute this. And so there was no hydrogen here, but we would get an alkene and IBr, which is a stable compound, and Br minus. This is a little unusual, and it's relatively rarely used, but one can see that this is also stereospecific because it's very similar to the mechanism of E2 reaction. However, these days this is not done so much anymore because there are better ways. So one of those better ways will be the use of zinc. And if you do use zinc in acetic acid, what we get is an alkene. Here we will leave stereochemistry unmarked, but this is an alkene which gives us zinc bromide as the atom material. And this is formally a reduction. And seeing this is easier if you just look at zinc, which was zinc 0 here, but it's here zinc 2. So zinc got oxidized, but an alkene got reduced. And then the third mechanism, and the one that we already seen, is the use of E1 reaction as an elimination tool. As we said already when we talked about E2, there are many problems with E1 reaction. The problems are rearrangements, and the occurrence of a cation, which is sort of a point where everything can diverge into either E1 or SN1 reaction. And so this reaction is not often desirable because cations can rearrange and then lead to undesired products. But in cases where cations cannot rearrange, or where we're already dealing with the most stable cation, this reaction works quite well actually. So if we had this dicyclohexyl system, then our first rate determining step would be elimination of bromide to give us a cation. And then this cation would then eliminate hydrogen to get to the most stable tetrasubstituted alkene. And so this would work as an E1 reaction, and I think this works in a relatively high percent yield. But again, given the choice between E1 and E2 reaction, you should always go for E2 reaction if possible, because those reactions are way more predictable and allow us to get products which are controlled both regiochemically and stereochemically. As a final note, if you do choose the E1 reaction, then tertiary and secondary substrates would work best. We would need a good leaving group, and we would need and basically any nucleophile or base would work. And this very loose requirements on nucleophile and base is what leads to the competition with SM. Now in the next subtopic we will see how we can use a completely different class of compounds, alcohols, as substrates for alkene preparation.